which statement describes the stability, right? We talked about stability of nuclei potassium atoms. We talked about why atoms are unstable versus stable. So who thinks they can give me an answer here? What's the deal with the stability of the nuclei of potassium atoms? Actually, hold on a second. I have to do this before I forget. Okay. What do we think? What's the answer? Here we go again. We really do need the Jeopardy music in this class. Yeah, I mean, I tried messing around with that. I did find one. All right, Three. Some potassium atoms have unstable nuclei that spontaneously decay. Who agrees with Pat? Majority. Okay. Who's not sure? All right. It's fair. Let's see, Pat. All potassium atoms have stable nuclei that spontaneously decay. What's wrong with number one? That's wrong. What's wrong? What's with the wording? They're stable. They don't decay. Right? All potassium atoms have unstable nuclei that do not. That's not true. Okay, that's not true. Not all potassium atoms are unstable. Okay, the ones on the chart are stable. So K39 is stable. Remember, 84 and higher is radioactive, unless we're dealing with isotopes. Like carbon 12, the one on the chart is stable, but carbon 14 is not. So when I say 84 and higher are radioactive, that's the ones on the chart, the ones that you see on the wall. Different isotopes can be unstable because of the ratio of the neutron to proton. Anyways, not all of them are unstable. Some potassium atoms have, that's what he thinks is right. Some potassium atoms have unstable that do not. Okay, so that doesn't make sense. If it's unstable, it will spontaneously decay. 3 is correct. Very good. The key here is some. Some potassium atoms have unstable nuclei that spontaneously decay. Not all atoms of elements spontaneously decay. Good job. Okay, next. Number 50, or no, yeah. One beneficial use of radioisotopes. This is common. Common question. It could be a short answer where you write your answer in, or a multiple choice, but this is a common question every year. Doesn't mean you'll have it this year, but it is common. They'll ask what's beneficial or give me one danger. So that they flip-flop. You know, sometimes they say what's beneficial or what's a danger. How's radiation dangerous? Something to that effect. And there's some things I haven't taught you yet, but you did watch the video. I also like to think you could kind of answer this without really, I mean, you just might know this from living, in other words. Maybe not, but I like to think this isn't something you have to get from me to answer this. Anybody have an idea? I mean, they said it in the video. That's why I'm throwing this out there. Any idea? It's okay if you get it wrong. Go ahead, Hannah. Yeah, number 1. Sometimes people drink or are injected with radioactive tracers, and it goes through their body, and then it emits radiation. And on a certain some type of scan, the doctors can see different areas have different amounts of radiation coming from it, or certain areas will almost like glow a different type of color based on that radiation, and they can see what's going on, see something that's wrong, or maybe not wrong. So detection of disease is a big one with radioisotopes. But let's real quick ask this question. If I drink a radioisotope for a scan, do I want that radioisotope to have a short half-life or a long half-life? So let's say I go to the doctor and I drink the radioisotope. I get it after school today. I drink it tonight. Tomorrow morning, I go get the scan. Do I want that radioisotope to stay radioactive inside me until I'm like 65 years old, or do I want it to decay and become more stable, like by Friday. That one, right? So short half-life. Some of you said that. So just keep that in mind. That's another question they will ask about that. Okay, so radioisotopes you use in your body. You want short half-life or long? Short, right? You don't want it to be radioactive for a long time. All right, so that's it. Just a little bit of warm up there. Good practice problems. Homework. Let's zip through it. I'm just going to read all of the answers, and I will take some questions, but I know sometimes we don't like to volunteer in here, so maybe I'll just go over some of them randomly, but here's all the answers. So the moral of the story with this, you're balancing the numbers on either side, right? So for the first one, I guess the first one I'll just explain quickly here. You have 42 for the top left number. Oh, Michaela, you have no idea what I'm talking about. Anybody else need this? You guys have it, right? Give that over to Michaela, please. Someone help her. Thanks. All right. So 42 on the top left. What's the bottom number for K? What's the atomic number? 19. So you should have labeled that to help you, right? To help yourself. So 42 over 19 yields 0 over negative 1e plus. So in the blank, the top number must be 42 because 42 plus 0 equals 42. Treat that arrow, you can as like an equal sign or the middle of like scales that are balanced, you know, however you want to understand, whatever's going to help you understand. The numbers on the left have to equal the numbers on the right. So 42 on top. The bottom number must be 20 in the blank because 20 plus negative 1 equals 19. So 19 on the left, 19 on the right. So now you go to your periodic table, look up number 20, and that's calcium. So in the blank, it's 42 over 20 Ca. Here's a pitfall. So I guess I'm going to go through this one a little bit slower. So this is what we have. I would always fill it in. If they don't give you the atomic number, look it up and fill it in. So here's a pitfall that students will fall into. They'll say, okay, they do the bottom number first. So they'll say negative 1 plus, oh, I know this needs to be 20, so that equals 19. Then they go to the chart and they say, all right, that's calcium. Guess what mistake they make now?
They use a number on the chart.
Right, they use that number, which is 40. So they do they do some good work. They get the 20. They look up calcium, and they're in a good spot. But then they just go too quickly, and they look up the mass, and they write 40 because that's on the chart. But remember, in nuclear chemistry, it isn't always the one from the chart because the number of neutrons are changing. So the mass number will change. The other thing to consider is the balancing. You got 42 here, that's not going to work. So really it's 42 here. So be careful. Please don't just write down the mass from the chart. The atomic number doesn't change, but the mass can because the neutrons changes. Okay? The neutron number can change. So just be careful with that. So I just want to go through that one kind of slow. All right, now I'm going to kind of rip through all the answers. Stay with me. If you get one wrong and you don't know why, please ask a question at the end. Number 2, 235 over 92U. Number 3, 4 over 2HE. Number 4, 4 over 2HE. Number 5, 3 over 1H. And you know what? I just decided that I want you to get together and share the rest of your answers. Slide together. Share 6 through 10. If you need help, help each other. If you don't have a partner, all right, Morgan, I can be a partner. Actually, Shane. Never mind. That's perfect. You two did good. Okay. All right. So number 6. I'll tell you what I got. So help each other. Maybe now you can if you got some wrong. 6. I got 1 over 0 and. You have to. So you knew that, but you didn't just have to share it. Okay, so go ahead, put a 0 in there. So now, what is that? What element has a 0?
So this had to be, because there's already 15, so it has to be a 1 instead of 0. Yeah, you're right, actually.
Yes.
230. Okay, I got 33. I just put 1 on 233.
You have three of those. 1 plus 1 plus 1. 241.
Sometimes I got mixed up. Sometimes
Stuff makes sense? Good. Okay, good. When you're done comparing, slide back, please. Okay, so I'm just gonna read through 6 through 10. 6 is unique because 6 is not an element, it's a neutron, 1 over 0 n. It's a neutron. That can happen, okay? You can have neutrons flying out of the reaction, especially if it's artificial transmutation. So if scientists are smashing things in labs, neutrons can come flying out. That's normal. Yeah, 6 is 1 over 0 n. The way you know it's a neutron is if you do the math, the bottom number has to be a 0. There's no element with atomic number 0. That doesn't make any sense. That means it wouldn't exist. You have to have at least 1 proton to be an element. So it's 1 over 0 n on table O. So if you knew it was 1 over 0, but you didn't know what to write, it's on table O, right? That's the neutron. So that's tricky. 7, 6 over 3 Li. 8, 37 over 18 AR. Number 9 is 235 over 92 U. The reason number 9 is 235 for the math is because of this here. That's 3 neutrons, so that's like 1 plus 1 plus 1. So if you look on the right side of number 9, you have 142 plus 91 plus 3. That adds up to 236. And then on the left side, you have 1 neutron, so that's 1 plus 235. So number 9 is 235 on top. 92 on the bottom, that's uranium, U. And then number 10 is plutonium, Pu, 241 over 94. So 241 over 94, Pu. Questions on those? Don't put them away yet. I got more